this video, we're going to take a look at our data that we collected in our previous video. We're going to organize it in tables, look at the graph, and talk about how the graph relates to the shape of the container. First container we did was container A. It's this thermos water bottle thing that my wife has. And we noticed that it has a very regular shape. It doesn't change. There's a little bulge here in the picture for some reason. I think that's just some kind of photo processing artifact. But it's basically just a straight tube. So as we fill water, the shape doesn't change, and so the fill rate, so the height of the water versus time, so the centimeters per second, is basically a straight line. It does change a little bit here. That's probably just a measuring mistake. That's fine. When we measure things in real life, they don't always exactly match what we predict, and that's okay. So that's probably just a data collection error. That's okay. We see I've taken the information here that was on our whiteboard that I wrote down. I've typed it up nice and neat, and we can see a nice linear trend where the height just increases regularly based on time. So that's what happens when the container shape stays the same as we go up. Container B. This was our Erlenmeyer flask, and we notice the shape does change. At the bottom, it's quite wide. As we go up, it gets narrower and narrower. And at the top part, it stays about the same amount narrow. So as we first start filling, the container is quite wide. So the height's not going to increase very quickly. The water has to spread out and go all the way to the left and the right to fill the whole width of the container. And so it doesn't change in height very quickly. But we notice as we get higher up in the container, the rate increases. And normally, if I do this at school in the lab, we use a container that, like a spout that doesn't fill so quickly, and we can get a little bit better data. But just because I'm working at home, we have to make do with what I have. So the shape of the graph isn't perfect, but we do see that partway through, the fill rate, the height versus time, gets a lot steeper. That happens when the container gets narrower. So it's a lot easier for the water to fill left and right away. So the only place it has to go still is up. So as our container narrows, the slope of our height versus time, or the rate at which the height increases. So narrower means faster change in height. Container C, this was our water bottle. And similarly, once again, notice that for the most part, it's pretty straight. And that's because most of our water bottle is pretty straight. There's no change in the width. It's just like a cylinder. So at the bottom, we have the bumps for the bottom of the water bottle. And we can kind of see the graph isn't quite straight there, so that's probably related to the shape of the bottom. This part's basically a smooth cylinder, just like our container A, so we get a nice smooth fill line at that point. And what do we notice as we get to the top of the bottle? Our slope starts to increase, kind of curves up a little bit here, and then curves up sharply here at the end. That's because the container is getting narrower. So we can see that this region right here might match this region right here. And here, as it gets very steep, that can match this region right here. So as the shape gets narrower, the curve increases and gets a bit greater slope. For container D, let's let this load. This is our Tim Hortons cup. What do we notice about the shape of the Tim Hortons cup? I like this graph. This is a pretty good reflection of what's happening. It's narrow at the bottom, and it gets wider as we go to the top. So here, the water doesn't have to go as far left and right. It's going to start going up pretty quickly. But as we get wider and wider near the top, it has to fill all the way to the left and the right, all the way across. And so the height decreases. So this part here, where it's filling pretty quickly, height's increasing pretty quickly, that might be this part right here. Here in the middle, it's filling pretty evenly. That can be this part right here. And here, as it starts to slow and fill even, and the height changes even more slowly, that's going to be our top here, where it's quite a bit wider than at the bottom. So as our shape gets wider, the slope of our graph decreases. Let's take a look at container E. This was our pop bottle. Let's start by looking at the shape. We got the feet at the bottom, so there's a little bit of a funky shape going on. As we go up, as we go up, it's basically like a cylinder. It's pretty smooth. There's a couple ripples and ridges. The shape changes slightly. And then at the top, we see that it gets narrower once again. So it's going to fill quickly when it gets narrower. So this part here, it's probably the part here kind of averaged out. As we get to the middle, it gets wider. And so our slope from here to here, this region right here, the slope is less. That's because it's gotten wider and it's about the same width, so it's going to have about the same slope everywhere. And then at the end, as our shape gets narrower once again, the fill rate increases, the height versus time increases, so it increases height more quickly. So remember, as it gets wider, the slope gets less steep. As it gets narrower, the slope gets more steep. And finally, F. I didn't actually measure at 1 second per fill. I just turned the tap on and off as quickly as I could. But just for the sake of making our graph, I'm assuming that each little spurt was about 1 second. What do we notice about this container? Well, it's narrow and it's uniform. It's a cylinder straight up and down. So there's no changes in width. So we would actually expect that we should have a nice straight linear line. As you can see, our data collection wasn't exact here. And I mean, I was going very quickly trying to turn the tap on and off because this filled very quickly. So it was hard to get a good measurement. So our graph is slightly incorrect. It should be straight all the way through. And we have a little change in slope here, but that's okay. Once again, that's a normal thing that happens when we collect data. Sometimes it isn't quite perfect, even though we know the cylinder is perfectly smooth and the same width all the way through. What other thing do we notice? I said back on graphs like this, that as our bottle gets narrower, the height changes quicker. This graph has a fairly steep slope compared with the rest. And we noticed that when I was filling it, I had to be very careful because it filled very quickly. So once again, this is another demonstration that as I as I have a narrow container, the change in height versus time is very fast. We can even compare this back with container A, which also had the same shape. It took 7 seconds to fill. The height versus time was lower. This was less steep because it was wider, so the height didn't change as quickly. With my other container that's very narrow, the height changed very quickly. So the graphs should have the same shape. They should both be a nice linear line because that matches the shape. But because this container is wider means less steep slope. So this slope here is not as steep as this slope here. It's kind of hard to tell. It's kind of auto formatted and we guessed at the numbers, but that's generally what we look for. So the shape of the graph tells us about the shape of the container, and the steepness, how steep the slopes are compared with each other, tells us how narrow the container is or how much wider the container is, relatively speaking. We're going to end this video here, and then I will work through a few questions from the homework sheet as well.